Hello everyone, welcome back. It's been a hot second. Had to finish some schoolwork and everything. Hope everyone's doing well. I imagine some people watching this are students. You just completed school, or you're just out for the summer. I'm also out for the summer, and that means I get more time to record this. Uh, well, since we last talked, I decided to change up the format a little bit. I thought it would be a better use of your time. Instead of watching me write things all the time, I'll just write the important stuff, and then we'll have more time to discuss examples, draw pictures and stuff like that. You know, all those seconds waiting for me to write something that can really add up. So let me know in the comments how you like this format. Maybe if you want me to go back to the old one, I can do that. But if this is more effective and you like it more, we'll stick with it. If you're interested, the software I'm using, it's called Obsidian. I just downloaded it, typed some notes up, got a custom, set up and designed so it looks nice. Nothing too special, but we're going to give it a try today. Now, since it has been a long time since we've talked, I would recommend that you review what an outer measure is, because we're going to be building off of that today. Also, by the way, if you hear a noise, someone's decided to operate the world's loudest buzz saw right outside my window today. So, I'd record later, but I just want to get a video out. All right, let's get to it. So we talked about this Lebesgue outer measure a while ago, and the idea is it's not a measure, it's an outer measure. So it's almost there, but we miss a particular condition, wink, wink, nod, nod, that we want measures to satisfy. Now, it is very nice because it's intuitive. The Lebesgue outer measure is. One of the reasons it's intuitive is that when we talk about measuring the size of the sets we know, like take the unit interval, the Lebesgue outer measure returns the number that we think should be assigned to the size of that set. So when it comes to the unit interval 0, 1, the Lebesgue outer measure is nice because it's Lebesgue outer measure of the unit interval. That's just 1. And in general, for an interval AB, what's the Lebesgue outer measure of that? Well, it's just B minus A, which is great. We got a couple of other nice properties, which the first one's translation invariance. Right? If I shift a set, I just pick it up, place it somewhere else. I don't add, take away, I don't stretch it or squeeze it. Well, that shouldn't change the size of the set. And what's great about the Lebesgue outer measure is it's translation invariant. You want to shift a set from here to there, it doesn't change the outer measure of it. Okay. I'll start walking you through things a little bit more rigorously. If I have a fixed real number, I'm going to define x plus a. A is a subset of R. As the set, I just take x, I add it to every element of A. All those points together is this shifted set x plus a. And the Lebesgue outer measure is translation invariant. That means that the Lebesgue outer measure of x plus a, it's still the Lebesgue outer measure of A. It doesn't change. And that's for any subset of R and any point x. The other thing that it satisfies, again, it's a really intuitive way of measuring things. It's monotone. So if I have two subsets of the real line, and one is quote-unquote smaller than the other, one is a subset of the other, well then the Lebesgue outer measure of the subset should be less than. There should be a less than or equals to symbol. We'll change that real quick. Just like that. Look how easy that is. They should pay me to advertise. The Lebesgue outer measure of the smaller set is less than or equal to the Lebesgue outer measure of the bigger set. Very simple. And then the third, we have countable subadditivity. And this is the only issue. This is the only hitch, which is we really want this to be an equal sign, but it's not. Okay, let me just do this so we're not bothered by, there we go, perfect. Countable subadditivity, digesting this definition. Okay, for any countable disjoint collection of subsets of R, the Lebesgue outer measure of their union is less than or equal to the sum of the Lebesgue outer measure of the parts. Now, we would like this to be equal. If this was equal, the Lebesgue outer measure would be a measure, but it's not. It's equal in a lot of the sets you think of naturally. Probably if you haven't taken a measure theory course and you're not a big nerd, pretty much any disjoint collection of sets, plug it into here, you'll get an equality. Okay, but it doesn't always hold. And there's these quirky little sets. They're called Vitali sets. I'll let you look those up, where you get a strict inequality here. So this will be strictly less than the sum in the case of Vitali sets. Okay, so we need to sort of rescue the Lebesgue outer measure from these sets, because we want a measure that's intuitive, measures things like this, gives us the size that we would expect intuitively that these closed intervals should be. We want that. We also want a measure, not just an outer measure. We want a measure that's translation invariant, also monotone, and we want countable additivity. If we want this to always be an equality, the solution is really simple, right? If we want M star, the Lebesgue outer measure, to define a measure over some sigma algebra, because in this case, M star is defined over all the subsets of the real line. All we have to do is be picky about the subsets of R we plug into M. So plug into M star. So literally what we're going to do is just kick these sets out and just not even act like they don't exist so that we get equality here. But let's talk about how we do that a little bit rigorously. So Cartheodory, I think that's French. I don't really know much about him, but he came up with this criterion for what sets do we restrict our attention to ensure that we have equality here. Okay, and we're going to call those sets Lebesgue measurable sets. Equality here, I think I just said that. And those are the subsets of the real line such that this condition holds. Now let me break it down for you what this is talking about. We can do that with a picture. See, isn't this nice? You don't have to wait 20 minutes for me to write something. Okay. So we want our set A to be measurable. Let's draw A. Let's say A is red. Looks like a peanut. Okay. Not really. Now, before you say, hold on, we're working on the real line. This is 2D. This works for n dimensions. This works to define Lebesgue measurable sets on Rn. It's kind of nicer for the sake of picture if I do things in 2D. And a lot of the things we're discussing today, by the way, so you know, generalize to Euclidean space. You might ask, well, why didn't you just phrase everything in Rn? Because we're not really going to be working with that for now. I don't know. Well, we will be touching in the two-dimensional Lebesgue measure when we get into chapter 1. But for now, for simplicity, we're working on the real line. But I'll be using visuals in R2. Just know it's like the same thing. I'm not screwing you over. So anyway, the idea is we're saying that this red set A is Lebesgue measurable if for any other set T, which may or may not intersect A, but let's consider the interesting case where it intersects A. It has a bit inside A and a bit outside of A. So here's T. We're saying that for all subsets of R, T, any, doesn't matter what it is, I can write the Lebesgue outer measure of T, the Lebesgue outer measure of T, as the sum of two parts. The part that it has in common with A and the part it does not have in common with A. So two parts. We can break it up into this. That's the Lebesgue outer measure of A intersect T, together with sum with the Lebesgue outer measure of what t has unique to itself that's not an A. So that's m star. T intersect A complement. You can also write this as, equivalently, T take away A. Okay? And we're saying that A, right? All this attention on the set T, but the whole thing's really about A in the end. A will be Lebesgue measurable if for any set T, whether it intersects A, whether it's disjoint from A, whether it's a subset of A, we have this equality here, right? And in that case, A is measurable. And we denote all of the sets A that satisfy this, all the set of measurable subsets of R by this cursive L right here. Now, if you really don't like this definition, and that's okay if you don't, you got what? You got 6 more to choose from. So let's just go through them. I want you to feel like, you know, Lebesgue measurability isn't all that scary and fancy. So we'll kind of discuss these, and you know, you can pick one. They're all equivalent. This is a theorem, right? The following all are equivalent. If a set A satisfies one of these bullet points, it satisfies all of them. Okay. We've just discussed the first one. That's the OG definition of Lebesgue measurability. We've got these two right here, which are quite useful. What they're saying is, in concept, like just take this second one here. For all epsilon greater than 0, there exists an open subset of the real line containing A such that the Lebesgue outer measure of that open set take away A is less than epsilon. And if A satisfies this condition, then it's Lebesgue measurable. What is this saying? This is saying that we can approximate our set A from the outside, right? Because the open set contains A. And the error of that approximation is less than epsilon. We can make the error as small as we want. So let me draw that in a picture. Again, we'll use the 2D case. We'll just draw things in 2D, even though we're technically working in 1D. You know, I hope this isn't too confusing. So here's A in black. And what this is saying is, okay, find, is saying, you know, given, write it up here, given epsilon, that's our error, you can view it that way, epsilon greater than 0, I can find an open set U, we'll call this U, which contains A, and the error, which is this red right here, right? That's U take away A. The Lebesgue outer measure of that is less than epsilon, right? And I can, no matter how small epsilon is, I can find an open set U containing A that approximates A within a tolerance of epsilon, with a Lebesgue outer measure of the difference smaller than epsilon. And then with the closed sets, it's the exact opposite. You're approximating A from the inside with closed sets where the error is less than epsilon. So we'll go ahead and draw that. Oh my goodness, what is that? I gotta do that. Getting used to this new setup that's been quite something. Okay, so to draw that, instead of bounding A from the outside, we're just gonna draw a closed set on the inside. So this third condition is, again, pick any epsilon greater than 0. I'm going to tell you I can approximate A from the inside by a closed set, and that error will be less than epsilon. Okay. All right. So let's say F here looks like a boot. Okay, this is F. Looks like Italy. Okay. So given this F, I'm saying I can find a closed set F such that this area here in red, this error, because F is not the same as A, right? We're missing some stuff. But the total amount of that missing stuff, which is the same as A take away F, the Lebesgue outer measure of that is less than epsilon. That's what that second condition is saying. We're going to come back to the third and fourth conditions now and move on to the fifth and sixth. These are really important ones. A set is going to be Lebesgue measurable if there exists a Borel set contained in A where the Lebesgue outer measure of the difference is 0. And you'll notice it follows immediately from this, and this is something to even write down, that all Borel sets are Lebesgue measurable. So we know that this set of Lebesgue measurable sets is huge, right? Just because we have Borel sets, we got open sets, closed sets, compact sets, all that stuff. So we don't really lose a lot of stuff when we restrict ourselves to the Lebesgue measurable sets in terms of useful stuff. Okay. So, and you can do it either way. You can say, okay, it'll be measurable if I can find a Borel set that is a subset of A where the Lebesgue outer measure of the difference is 0, or there exists a Borel set containing A where the Lebesgue outer measure of the bigger set minus the smaller set is 0. So you can do that either which way. The most important consequence of this is that you need to see is that every Borel set is Lebesgue measurable. Okay. Now for these last two. There exist open sets, U1, U2, all containing A, where that the Lebesgue outer measure of the intersection of all of those open sets, remember, each of them contain A, so A is an element of this. The difference between that and A is 0. We'll do a quick computational example. I don't think we'll really be using these. They might be helpful in some proofs. But we're just going to cover one of these and move on. Take, for example, we want to prove or want to show that the closed unit interval is Lebesgue measurable. And we're going to use this definition right here. What do we need first to prove? We need a collection of open sets, all of them containing the closed unit interval. We need that first. Okay. Well, I already know what it's going to be, so I'm not pulling it out of thin or anything. Okay. I'm going to say define my UN as follows. I'll take the nth term of the sequence to be the following open interval, right? Indexed by n, we'll have our left endpoint as -1 over n, and my right endpoint will be 1 plus 1 over n. What happens when n goes to infinity? This guy will go to 0. And this guy will go to 1. Now notice that this is a decreasing sequence of sets. That means as n gets larger and larger, the set gets smaller and smaller as it wraps around the unit interval 0, 1. So you can kind of view it like this. If the page stops moving around on me, take real line, take the unit interval 0, 1. What's happening here as n goes to infinity? It's like this. It starts wrapping around. Okay. And notice that the unit interval is contained in each of these UN. Great. And it actually turns out that the intersection of all of these sets is the closed unit interval, 0, 1. Okay. But that's not what we require. Notice that in this definition. We're not requiring that the intersection of these open sets is equal to A. All we're requiring is that the difference has Lebesgue outer measure 0. That's it. And it indeed does. I mean, if we compute this, right, if I just start with computing this set inside here, This is A itself. Okay, so this is actually just the empty set. Even though this, just because this is 0 does not mean this is the empty set. Okay, keep that in mind. So, but in this case, the Lebesgue outer measure, excuse me, of the empty set is 0. So we conclude that the closed unit interval is Lebesgue measurable. Okay. And then this is just the, again, open sets we come from the outside. Open sets we come from the outside, closed sets we come from the inside. That's what we're doing here. Okay. You sort of grow. You just have closed sets contained inside A. And if the Lebesgue outer measure of A take away the union of all of those closed sets is 0, then in that case, A is also Lebesgue measurable. These are all equivalent conditions. You can use whichever one you like. The textbook that we're using presents Cartheodory's criterion, so expect that would get used in proofs. But if you find a way to use the others, if you like using the others and thinking of things like that, there's nothing wrong with that. So I hope you at least understand one of these definitions. That's sort of, I would say, if you don't, I would pause, ponder over these, look for some examples. I'll reference you, by the way, while we're here and review. This guy, Sheldon Axler, he has a book called Measure, Integration, and Real Analysis. Very, very well written book. It's available for free online as a PDF. You just look up this, plug this exactly into Google, and you'll find a good book. You can practice these definitions, practice proving some things, maybe practice a couple computations, and he's got some examples in there that would help out a lot. Okay? So, what's the conclusion of all of this? Well, so we now have kicked out these weird sets that don't give us countable additivity for the Lebesgue outer measure. The question is, did we make a mistake? Did we kick out too many and our set sucks and it's not very nice? Well, no. The set we get, the set of Lebesgue measurable sets, is a sigma algebra over the real line. You can prove this if you want. I'm not going to for the sake of time. I don't want to keep you here too long. But it turns out that the collection of all Lebesgue measurable sets defines a sigma algebra over the real line. Great. And with that, what we're going to do now to get our countable additivity to work always, like I said earlier, we're just going to consider the Lebesgue outer measure over the Lebesgue measurable sets. And if we do that, we get a measure. We get a measure that's translation invariant, that's monotone, and really importantly, countably additive over disjoint countable collections of sets. So that's what we do. We use the following notation. I'll have M denote the Lebesgue outer measure restricted to Lebesgue measurable sets. And this is a theorem. Right? This is to be proven. This defines a measure over the sigma algebra of Lebesgue measurable sets. And we call M the Lebesgue measure over R. Very simple. It's nice. Now, sometimes, in some cases, we're going to want to restrict our attention to closed intervals. And so all you do is you just restrict the Lebesgue to define the Lebesgue measure on a closed interval. All we're going to do is restrict the Lebesgue measure to the following sigma algebra. Okay? And that sigma algebra is what? It is the power set of the closed interval intersected with the collection of Lebesgue measurable subsets of R. What is this in one line? This set is all of the subsets of the closed interval that are Lebesgue measurable. So all we do to define M, the Lebesgue measure on the closed interval, is restrict the Lebesgue measure over R to the sigma algebra here. Pretty straightforward. What's next? We have some terminology to keep in mind. We're going to be using these words a lot. about some things that have Lebesgue measure 0. You know, the set of points where the function is discontinuous has Lebesgue measure 0. We're going to be talking like that. Okay? We say that a subset of the real line, it has Lebesgue measure 0 if for any chosen epsilon greater than 0, there exists a covering of A by intervals where the sum of the lengths of those intervals is less than epsilon. Okay, what is that in symbols? We have this open covering of endpoints, AI, BI, indexed by the naturals, with two things. The first one is that this collection of intervals covers A. And then the second is the sum of the lengths of the intervals. Remember that the length of an interval is the difference between the endpoints. It's the right endpoint minus the left endpoint. The sum of that is going to be less than epsilon. Let's look at perhaps the most bare bones basic example. Proving that a set containing a point has measure 0. Okay, you can pick any point you want on the real line. I'm going to pick 0. And I want to prove that the measure of that set is 0. Again, look at how great the Lebesgue measure is. You would think it's 0. It's just a point, you know. It's really unimportant, so it should have measure 0, but we got to prove it. Okay, it's really easy to do. So to prove that it has measure 0, okay, for all epsilon greater than 0, okay, we're just going to let epsilon greater than 0 be arbitrary. Okay, just arb. It's not arbies, that means arbitrary. Okay. What do we need to do next? We need to find a covering of A, a covering of this set containing 0, by intervals whose sum of lengths is less than epsilon. Well, this is just a point. You really don't need to work hard to cover it. We can just cover it by one interval and call it a day. Okay, but we need to choose it intelligently, so it needs to have a length. We're just going to pick one, a cover with one element. We need the length of that interval to be less than epsilon. Okay, well, let's see. Maybe what if I just pick an open interval around 0, right? Let's draw it. And all I need is the diameter d to be less than epsilon. Seems pretty straightforward to me. So what we'll do is, you know, if we want it to be symmetric, we'll just say, let's have r less than epsilon over 2. Okay, so putting this back in the proof, we have r epsilon greater than 0. You gave me one. We're going to cover the set containing 0. Again, this extends to any point on the real line by the open interval. We'll say negative r over 2, or excuse me, negative r, because that's our radius, r, right? And that obviously contains 0. Okay. Now, what's the last thing we need to check? Does the length of that interval, is that less than epsilon? Well, it is, because of how we chose our diameter, or that's 2r, you know. We chose our diameter, which is equal to 2r, to be less than epsilon. Well, what's the length of this? Well, it's going to be r minus negative r, which is 2r, which is equal to our diameter d. This really wasn't needed. We could have just been direct, but whatever. And that's less than epsilon. And we're done. So a point has measure 0 as you'd expect. Now, what's also important to keep in mind, and I'll let you prove this as an exercise if you're new to measure theory, it turns out that all finite and countable subsets of the real line have Lebesgue measure 0. Okay, so the natural numbers, they have Lebesgue measure 0. The set containing 1 and 5 and pi has 3 elements that has measure 0, Lebesgue measure 0. Okay. Now, sometimes we have a condition that we have set a proper, like for example, we have some function and we want to talk about the points where that function fails to be differentiable. And, sets of Lebesgue measure 0 are kind of just unimportant, right? We assign them a measure of 0. They're not really, it's basically a way of saying we can just not care about it. For all intents and purposes, we can just basically not care about it, kind of. There will be some people who get really upset at me saying that, but they're pretty unimportant, sets of Lebesgue measure 0. And sets of Lebesgue measure 0, they imply some language talking about almost everywhere and stuff that we're going to be using. So to motivate it, take, for example, this translation of the absolute value function. We'll say x plus h plus y. No, I think people usually use k. Here's my f. Okay. Now, an example of using this almost everywhere language is like this. Okay. If we want to talk about where f is differentiable, okay, and you just look at this, you're like, okay, well, it's differentiable here, it's differentiable here. Oop, you got a corner, but the corner is just 1 point. Okay, it's just it's 1 point on a continuum of points where f fails to be differentiable. Not really important, right? And so we say that f, okay, it's pretty much differentiable, right? It's differentiable everywhere except for this annoying point at the vertex. Okay, so how do you say that professionally and not like a slob like I'm saying it? You say that f is differentiable almost everywhere. Okay, so the idea is if I have a property, looking at it down here, p, input's a real number and output's a Boolean, true or false, if that denotes some property, then we say that the property holds almost everywhere if the set of points of real numbers where the property does not hold has a Lebesgue measure 0. So in this case, what's our property? Our property is p of x is if I input x, it outputs whether or not my function f is differentiable at x. Okay, so the set of real numbers where that property is false is precisely the set of real numbers where f evaluated at those real numbers is not differentiable. And that's for this case. So that's what we mean by that. Now, we can also define this generally, given any measure, not just the Lebesgue measure. So for a general measure mu over a measure space x, sigma algebra measure, we say that a property p of x holds mu almost everywhere. We might chop off the mu if we already know what it is. If the set, again, where that property of points where the property does not hold is contained in a set with mu measure 0. This definition implies the first. Okay, so yeah, that's it. Let me think if there's anything else. Maybe I should cut this out, or maybe I won't. That's it for today, or this video. I'm going to try to record more today. Just to show you what's coming up, we've got 3 more videos before we get there, okay? I'm sure you're probably excited to get past all the reviewing. So here's what we're going to do. We just did this one. Next video, we're going to talk about Lebesgue integrals. Very, very simple. Then we're going to talk about convergence theorems. This is like the pinnacle. This is the climax of this movie. We're going to talk about the monotone and dominated convergence theorems, which are really fun, super useful, and extremely important. So 9 is one to really, 8 and 9 are ones you need to lock in, really pay attention to. A lot of this abstract measure theory, we're not really going to use too much. What we really care about is being able to know how to work with Lebesgue integrals, being able to apply and use the convergence theorems. Okay. And then after that, we're going to have a one video crash summary of some important stuff from complex analysis, going all the way from holomorphic functions to integral theorems, contour integrals, discussing some theories, series stuff. What that video is going to be is me just on one part of the screen. We're going to have a cheat sheet for complex analysis, something you would type up for an open notes exam. And then on the other side, I'm just going to be doing examples to illustrate those concepts. Okay, so we're not going to draw out a complex analysis review. It'll just be one video. All right, that's it. I'll see you guys in the next one. Thanks for watching.